Hello everyone, my name is Ines Brooks, and today I will be presenting the Data 690 Capstone project titled Enhancing SOC Alert Prioritization Using Machine Learning. This project explores how supervised machine learning techniques can be applied to improve the way Security Operations Centers, or SOCs, manage the overwhelming volume of cybersecurity alerts. Let's begin. The scope of this project was to build a machine learning model that classifies cybersecurity alerts into three categories: true positive, benign positive, and false positive. The aim was to improve triage efficiency in security operations centers by reducing manual effort and alert fatigue. I also focused on delivering a solution that is explainable, scalable, and trustworthy. Security analysts face overwhelming alert volumes, over 70% of which might be irrelevant. These false positives consume time and delay the response to real threats. Manual triage is often inconsistent and slow. Our guiding research question became, can machine learning reduce triage efforts and improve accuracy in classifying cybersecurity alerts? Cyber threats are increasing in both frequency and sophistication. It's critical for organizations to reduce mean time to detect (MTTD) and the mean time to respond (MTTR). This project supports broader enterprise goals in automation and security governance. It also aligns with the responsibilities of a Chief Data Officer (CDO), emphasizing proactive, data-driven threat management. To begin addressing this challenge, the Microsoft Security Incident Prediction dataset from Kaggle was used. It includes over 13 million roles and 45 plus features such as timestamp, alert ID, and entity behavior. The target variable, incident grade, has three classes: true positive, benign positive, and false positive. True positive represents actual critical alarms, benign positive refers to no critical issues, and false positive covers false alerts. The dataset captures telemetry and detection scenarios reflecting real enterprise SOC environments and presents a class imbalance that poses additional challenges for accurate classification. Next, let's look at the tools and the methods I used in the project. The analysis was conducted using Python on Google Colab. For data wrangling, pandas and NumPy were used. Visualization was done via Seaborn and Matplotlib during EDA. Three different machine learning models were created on this data: logistic regression, decision tree, and random forest. Finally, hyperparameter tuning has been done to enhance the performance and the generalizability of the model and identify the champion model. Before jumping into modeling, some visualizations from the data were reviewed. The exploratory analysis provided several key insights. The focus was on checking the distribution of the incident grade, alert ID, and the weekend features. These visual cues highlighted the importance of including temporal and categorical features in the machine learning pipeline. This chart shows how alerts are distributed across the three target classes. The clear imbalance reveals that benign positive is the most frequent label. This insight influenced the use of class weighting and inspires careful consideration of evaluation metrics such as weighted F1 score to avoid bias towards the majority class. This histogram shows how often each alert ID appears in the dataset. Most alerts are clustered at the lower end of the ID range, meaning a small number of alert types are triggered very frequently. This likely reflects repetitive or automated system behavior, which is typical in enterprise environments. This comparison highlights how alert categories vary between weekdays and weekends. Greater alert diversity was observed during weekdays, reinforcing the value of including temporal variables to improve classification accuracy. Let's now move into data preparation phase. To prepare the dataset for modeling, several preprocessing steps were performed. Since model training, especially during hyperparameter tuning, was taking a considerable amount of time, the dataset was subsampled to 1 million records while preserving the original target distribution. A Pearson pairwise correlation analysis was conducted to identify and remove highly correlated redundant features. Categorical encoding was applied to convert non-numerical variables into suitable numerical formats. Finally, minimal scalar was used to normalize numerical values across all features to ensure uniform scaling. Here we can see the heat map of the pairwise Pearson correlation value. Higher absolute values show more correlation between the two features. By setting the threshold of high correlation to the absolute values higher than 0.7, features like account UPN and account name are both highly correlated with account seeds. This shows that the information that those two features can provide is also available in account seeds. So, two features were dropped from the data. This step was essential to reduce redundancy and model training time. Machine learning algorithms cannot process categorical values directly. So, categorical features were converted into numerical format using two different encoding techniques. One hot encoding was applied to the evidence row and the weekend features as they contain a small number of unique values, and this method does not significantly increase the dimensionality of the datasets. In contrast, ordinary encoding was used to the target variable incident grade as well as the category and entity type features. These variables have a large number of unique values, and applying one hot encoding to them will have drastically expanded the feature space, increasing computational complexity. With the data now cleaned, encoded, and scaled, it's ready for model training. As the final step, the target variable incident grade was separated from the features. The dataset was then split into two sets, a training set and a testing set, using a 70-30 ratio, 70 for training and 30 for testing. Three classification models were selected for training: logistic regression, decision tree, and random forest. Initially, each model was trained using default hyperparameters, and they underwent the hyperparameter tuning process as well. a huge number of different hyperparameter combinations were created. Still, due to the time limits, only a subset of 20 different hyperparameter combinations for each model was randomly selected and tested using a five-fold cross-validation approach to ensure broader applicability. To make sure features contributed equally to the model, the feature values has been normalized using a minimal scaler. This transformation rescales all numerical features to fall within the 0 to 1. To prevent data leakage in the test set, scaling was first applied to the training data and the learned parameters were then used to normalize the test data. Let's start by looking at the default logistic regression model, which will serve as our baseline. As we can see, the model performs poorly overall with an accuracy of just 58%, a weighted F1 score of 54%, and a macro AUC of 0.73. The confusion matrix highlights its main weaknesses. It struggles significantly with the false positive class, where recall is only 9%, while performance on benign positive and the true positive is somewhat better but still limited. The ROC curve further confirms its lack of strong separation between classes, showing why more complex models will be needed to improve these results. Now, we are looking at the tuned logistic regression model. We notice almost no change from the default model. Accuracy remains at 58%, weighted F1 stays at 54%, and the macro AUC is still 0.73. The confusion matrix shows the false positive class continues to be overwhelmingly misqualified as benign positive, and ROC curves overlap almost exactly with the previous slide. In short, hyperparameter tuning here yielded no real improvement, confirming that logistic regression isn't powerful enough for this task. Now, attention shifts to the default decision tree, which delivers outstanding results. Both train and test accuracy hit 99%, and precision, recall, and F1 score for every class are also 99%. The confusion matrix shows only a handful of errors, fewer than 500 per class, indicating almost perfect classification. This is confirmed by the ROC curves with both micro and macro IUC at 0.99, demonstrating the model's excellent ability to distinguish all three classes with minimal bias. Now we are looking at the tuned decision tree. Test accuracy is 97% with precision, recall, and F1 all at 97 across classes. The confusion matrix shows slightly more errors than the default tree, especially a few hundred extra misclassifications of benign positive and true positive into other labels. Yet, the ROC remains perfect, micro and macro AUC of 1.00. This tells us that despite flawless ranking of instances, the tuned tree thresholded decisions are marginally less accurate than the default models. The tuned models' reduced performance compared to the default version stems from the small subset of hyperparameter combinations evaluated during the tuning process. Now, let's look at the default random forest. This model achieved 99% test accuracy with macro and weighted recall precision and F1 scores all between 98% and 99%. It also delivers perfect ROC curves, with both micro and the macro IUC at 1.00. The confusion matrix shows only a few hundred misclassifications per class, mostly in the majority benign positive group. This proves that the model's use of bootstrap sampling and random features selection creates stable, balanced performance across all classes without any tuning. Finally, the tuned random forest shows a significant drop in performance. Test accuracy falls to 70% in the micro IUC drops to 0.91. The confusion matrix reveals substantial misclassification of both true positive and false positive samples as benign positive, and many benign positive samples misclassified as false positive, indicating less clear class boundaries. Again, this reduction stems from tuning over a very limited hyperparameter subset, which degrades its ensemble robustness and ranking ability compared to the default models. This slide summarizes the overall evaluation of all 6 different models. As we can see, 3 models are dominating the other ones in terms of performance: default decision tree, default random forest, and tune decision tree. The default decision tree scores 99% across accuracy, recall, F1 score, and AUC. The other 2 models are showing comparable results to the default decision tree models, but in order to select our champion model, let's take a look at the KPI sets for the project and make our selection accordingly. This slide presents the 4 key performance indicators or KPIs that were used to guide model evaluation and selection. These metrics were carefully chosen to reflect both technical performance and practical relevance in Security Operations Center or SOC environments. First, the weighted F1 score threshold was set as 85%. This metric balances precision and recall across all classes weighted by their supports. It's especially variable in unbalanced datasets like this one, where relying on accuracy alone will be misleading. Second, recall for the true positive class was set to a minimum of 90%. This ensures that the majority of real security threats are correctly detected, minimizing the risk of missing high-severity incidents. Third, precision for the false positive class needed to exceed 90%. High precision in this category helps ensure that flagged alerts are truly relevant, which is essential for reducing analyst fatigue caused by unnecessary investigations. Finally, the false positive rate, or FPR, was required to stay below 5%. This matrix is calculated as FP divided by the sum of FP and Tn. Keeping this rate low means the model avoids over-alerting on benign activity, which is crucial for maintaining trust in automated alerting systems. Together, these KPIs form a rigorous framework for selecting a model that performs well both statistically and operationally in real-world cybersecurity environments. Computing those KPIs for each matrix will get this table. At the top of the table, we see that the default decision tree model achieved the highest weighted F1 score of 99%, true positive recall of 99%, and the false positive precision of 99%, with a very low false positive rate of 1%. These results clearly satisfy all the defined KPIs and indicate exceptional classification performance. The default random forest as well as the tuned decision tree models also perform well and can be used as alternatives with good performance for KPI sets. On the other hand, the tuned version of random forest and both versions of logistic regression models failed to meet the conditions. Given this comparison, the default decision tree model was selected as champion model for its strong performance across all key areas and its simplicity in interpretation and deployment. A feature importance analysis was also conducted for the champion model. This step identifies which input features had the greatest influence on the model's classification decisions. The most important features by far was org ID, contributing over 50% of the total decision-making weight. This indicates that alerts vary significantly by organization and that org ID plays a central role in distinguishing between alert categories. The next two features were alert ID and incident ID, each contributing roughly 15 to 70%. These variables capture the unique identifiers of alerts and incidents which likely reflect recurring patterns or non-threat types. Now let's talk about key findings. Decision tree-based models appear more effective for the task. Logistic regression fails to linearly separate records by label, making it unsuitable for the dataset and objective. Key predictive features for the classifier include org ID, alert ID, and incident ID. The final model demonstrates real-world utility in SOX by improving alert triage efficiently with accurate and swift classifications. Looking back on the project, here are some key takeaways. Data cleaning is crucial. Duplicate and missing label reduce quality. Unbalanced classes require mitigation strategies. In this work, class weighting was applied, but in some cases, upsampling and downsampling techniques should be applied to make the dataset balanced during the training. Applying feature engineering is an important step to prepare our data for model training. Each task might require different type of models, so training, testing, and tuning different models on the same dataset is a must. This model has practical relevance in multiple real-world scenarios. One major use case is cybersecurity alert triage. Platforms like Azure, Sentinel, and Splunk have shown that similar models can cut review times by up to 60%, helping reduce analyst fatigue. Another important application is in fraud detection. For instance, PayPal and JP Morgan Chase use machine learning to reduce false positives by about 40%, resulting in significant financial savings. Additional examples are shown in the slide, further demonstrating the model's broad utility across domains such as security operations and incident response. To build upon this foundation, future work might include using neural networks, deep learning models to improve prediction, trying different related datasets to validate generalizability, deploying the model in real-world environments to assess practical performance and business value. That concludes the presentation. Thank you for your attention. If there is any questions, I will be happy to answer them. The references used for this project will be displayed in these following slides.